Okay, today we are going to start Unit 6, which involves rectilinear motion. Okay, linear motion. So we're moving along a line. Okay, back and forth, left and right. Okay. You have probably worked with like position versus time graphs in science. Maybe some velocity versus time graphs. Maybe some acceleration versus time graphs. Okay. All three of those have you seen in physics? Okay. Welcome to the calculus side of it. Okay. Those of you who are in physics, you are not at a disadvantage. Okay. But those of you who are in physics, this may help put it all together for you as far as like the calculus with it. Maybe it will. I don't know. Okay. So what's happening is we're going to have some situations where a particle is moving back and forth along a line, hence the linear motion. Okay. We are going to graph these on, like I said, position versus time graphs. Okay. So the s-axis is the coordinate line that the particle moves along. The t-axis denotes time. So I know this is weird, but s is going to denote position. Okay. I don't know why s, but s is going to be our position. Okay. So we're going to be moving along the s-axis as far as we're going to be moving left and right. Okay. So S of t is going to be what our position is. And we're going to be looking at position versus time. Okay, so time is going to be our independent variable, okay, which is the same as what axis that you're familiar with. And the xy axis, which one's the independent variable? X, okay. So t is our independent variable. Position is going to depend on time, right? Okay. Instantaneous velocity. Instantaneous. We've seen that word.
Derivatives.
Okay. The instantaneous velocity is the rate at which a particle's position changes with respect to time. What does that sound like? A derivative. The rate at which a position changes with respect to time. Okay? So, given a position, if we find the rate of change of position over time, we're talking about the derivative. Okay? So, S of t is our position. If we take the derivative of our position, that is going to represent our velocity. Okay, the change in distance over the change in time, right?
On the second derivative,
Yes, indeed. Now, what is, okay, we have this word velocity and we have this word speed. What's the difference?
velocity has direction.
Velocity has direction.
Right.
So if I want speed, how would I get speed?
Just take the direction
Okay. Absolute value of velocity would be considered our speed. Okay. Now we are going to be talking about a particle moving right and left, back and forth. Okay. What is it going to mean when we have positive velocity?
as the object is moving right.
Because we are increasing our position. Negative velocity would mean we are moving left because we are decreasing our position. Now, I don't know if you've noticed, but in your book, we have had problems we skipped over that deal with motion. What I like about saving this till the very end is we can bring it all back together, okay? We are going to do derivatives and antiderivatives all together in this unit, and we're going to combine it all with what they need together, all right? So it's going to be a lot of fun. Okay, so the first thing I want to look at is a position versus time graph, okay? Here we have our position is t cubed minus 6t squared. Okay, so this is our position versus time. So let's talk about what this means. If this is the position versus time, okay, we are beginning at the origin. What is happening from 0 to 4? Okay, now this is our position, so this is mapping out our position. Okay, so if we, if we are decreasing our position, that means, first of all, our velocity is negative, correct? Which means we are moving left. So from 0 to 4, we are moving left. Okay, and then what happens from 4 to 7? We change directions, and now we are moving right. Okay, if I'm looking at a position graph, how do I tell where the direction changes? At a critical point. Okay, what's the slope at this critical point? 0. Okay, our derivative of position is velocity. What does it mean when your velocity is 0? You're standing still. In order to switch directions, we have to stop and then come back, right? Okay, now, not every time when our velocity is 0 do we change directions, but when our velocity is 0, with our position, we go from decreasing to increasing. Okay, we're changing position. Okay, what does it mean when our position crosses the t-axis? Well,
You're in the same position you were at the 0 second.
okay,
Or 0, whatever time you're going.
let's call it, let's say
at 0 time.
at t equals 6, we're at the origin. Okay, coincidentally, also at t is 0. Now, not all the time will we start at our point of origin. Okay, when I talk about point of origin, we're defining a certain place where your distance is 0, right? Not all the time will our particles start at that origin,
Yeah.
right? Okay. Now, we are going to take this and we are going to find its derivative. So first of all, please look at that equation. In your head, think about the derivative. It's nice and polynomial for you. Okay. Raina, what's our derivative?
Oh my God, I'm so sorry. 3t squared minus 12.
Do you agree?
Yes.
Okay. That is our velocity function. We took the derivative. So no, we're now at velocity. I'm not sure why Nolan is writing this down. Okay. So our velocity function, the derivative of position, is 3t squared minus 12t. Okay. So what does this mean? Okay. Let's first of all, let's look at these intercepts. So I see that we have t-intercepts, or x-intercepts, if you want to think of them, at 0 and 4. What is happening at 0 and 4? Okay. Kayla, what did you say?
I said switching directions, but it's not right.
Okay, well let's think, you are on the right track. We're looking at our velocity graph.
Yeah.
At the x-axis, that would mean what about the velocity? Right, okay. We have a height of 0, so this means our velocity is 0. Which means the particle has stopped, right? Now, how can we tell if it changed directions? Okay, notice how it crosses the x-axis here, right? We go from a negative derivative to a positive derivative. So we go from negative velocity to positive velocity. So first of all, okay, I know we already talked about when it's moving right and left, but it's important that we see it in this graph as well. From 0 to 4, we said that it was moving left. In the velocity graph, how do we relate that? What? Okay, yes, and how can we tell from this graph? Good, when our velocity is negative, so when our velocity is below the x-axis, right, we're moving left. From, well, this kind of cuts it off at 6, I'm still going to stick with 7. From 4 to 7, we're moving right, and we know that because our velocity is positive. Our velocity is above the x-axis. Okay. Now, let's talk about speed. How do we find speed? The absolute value of velocity. Now, when we take the absolute value of anything, what happens to its sign value? Everything becomes positive. So anything that is negative becomes positive. So here is what that graph would look like. Anything that was negative is now turned positive. So here is our speed. So where is our speed increasing? 0 to 2, and I've been using 7, I'm going to say 4 to 7. Okay, our speed is increasing there. Our speed would be decreasing from 2 to 4. There's going to be an easier way to tell if our speed is increasing or decreasing, and that is if we look at what? Okay. Okay. Jared already mentioned something about acceleration. Do you think the second derivative is going to be acceleration? What is acceleration measured? Okay. Acceleration is the rate of change of velocity, right? Which means if the acceleration is the rate of change of the velocity, we're talking about the derivative of the velocity. So, S of t is our position. The derivative of s is our velocity. You can think of this as the second derivative of position, or the derivative of velocity is going to be our acceleration.
Can we see it in any one of those forms? Like you could put S double prime T or A of T, and like.
I want you to define it as A of t, but you're going to find it by taking the second derivative of x. Does that
So,
make
so
sense?
like on the AP test, will we see find like a should mess you up like a find the derivative of B of T or find the double or second derivative of.
Well, what you need to understand is how position, velocity, and acceleration all relate together, so that eventually we're going to be able to go from position to velocity to acceleration, and from acceleration to velocity to position. Okay, does that help? Yeah. All right. So now, acceleration can tell us whether we are speeding up or slowing down, but it also has to deal with velocity. It's not just about whether we have positive or negative acceleration. It's about what's happening along with positive or negative acceleration. Okay? So how would we describe if we are speeding up?
Our velocity is increasing.
And okay, so our velocity is increasing.
Yeah, so the rate of change of velocity would be positive, and then velocity would also be positive.
Okay. What about if we have negative velocity and negative acceleration?
You only left it faster.
Okay. So if velocity, okay, did everyone hear Aaron? He was kind of quiet. Okay. If we are having a, okay, say that for, yep. You said it so nice.
The rate of change of velocity is positive, and then velocity would also have to be positive.
Okay. So if our acceleration and velocity are both positive, then we're speeding up in the same direction, right? If our rate of change is negative, as well as our velocity, then we're speeding up in the negative direction. So as long as our velocity and acceleration have the same sign, our particle is speeding up. Okay, so I'm going to come back to this picture here. We said that our particle had increasing speed from 0 to 2, right? Well, if we look at this piece from 0 to 2, this is our position graph. We are concave down, which means negative acceleration, and we are decreasing, which means negative velocity. So our signs are the same with velocity and acceleration. We're speeding up. Okay. From 6 to 7, we are, or I guess from 4 to 7, we are increasing, which means positive velocity. We are concave up, which means positive acceleration. So we're speeding up. Okay. Now, in the opposite sense, if you will, if velocity and acceleration have different signs, then our particle is going to be not speeding down, slowing. Okay. This is something that right now seems so simple, but it's going to be very easy to forget. So make sure you make a note of it somehow. Okay. This will be something that I will ask. And the only justification I'm going to accept is when you compare the sign values of velocity and acceleration. Okay? All right. Okay, so let's talk about, here is, I forgot I had this slide, here's the picture that I went way back to look at, right? So here's our position versus time. All right, here's something we haven't, well, let's talk about the acceleration. Our velocity was 3t squared minus 12t. What would the acceleration be?
6t minus 12.
6t minus 12. Here is that picture. Okay, so we have negative acceleration from 0 to 2 and positive acceleration from 2 to 7. Okay, let's talk about the other chunk of the graph that we haven't. From 2 to 4. Okay, you can see in our position graph that we are concave up, right? We have positive acceleration. We are also decreasing, which means our velocity is negative. We have opposite signs, so that means we are slowing down in our speed. Okay. Does it make sense that we're slowing down and then speeding up here before and after 4? Okay, because we're going different directions, right? Great. Awesome, awesome. So, here I have a function. Go ahead and write it down. Our position is represented by t cubed minus 21t squared plus 60t plus 3. We are going to analyze this motion. So, first of all, let's find the velocity. It's going to make this easier, right? What is our velocity?
6t squared.
Okay. And what would it be helpful to find from this? Our critical points. Let's find that. So we set this equal to 0. I'm going to go ahead and factor out 6. And what should we do? We can factor this to t minus 5 times t minus 2. So we have critical points at t equals 2 and t equals 5. They will usually give you units, okay? Most often we're going to be in feet and seconds. Okay, there's no units on here, so we're not going to worry about that right now. All right. What does it mean? What is happening at time is 2 and 5?
The velocity is 0.
Which means?
That we are standing still.
Okay, our velocity is 0, which means our particle is stopped. No, because then our particle wouldn't be able to move on. Yeah. Great question. All right. Now, let's look at our sign chart. Our critical points are at 2 and 5. What's happening to the left of 2? Are we positive or negative? To the right of 2. To the right of 5. Okay. So, what does this mean? When are we moving left? We're moving left between t equals 2 to 5 because our velocity is negative. When are we moving right?
0 to 2.
Good. That's all that we can get from velocity right now. Okay, let's also notice that when we are standing still, that is when we are changing direction, right? In this case, because we have the change in sign values. Now let's talk about our acceleration. Our acceleration would be what? You were ready with that one. 12t minus 42, right? Let's go ahead and find where the acceleration is 0. I'll try that again.
Yeah, T is 42 times.
So 7/2,
Sure.
right? Okay. So 7/2. What's happening to the left of 7/2 as far as acceleration goes?
It's negative.
To the right?
Positive.
Positive. Okay. So our sign chart has gone. I'm going to copy. This is our velocity, right? This is our acceleration. So our velocity sign chart was at 2 and 5 was positive, negative, positive. All right. So let's talk about when is our particle speeding up? Okay, from 2 to 7/2, both are negative, and from 5 to infinity, both are positive. When they have the same sign, we are speeding up. When they are opposite signs, they are slowing down. So you notice from 0 until 2, we have opposite signs. And between 7/2 and 5, we have opposite signs.
When velocity is negative and acceleration is negative, why is it speeding up?
Because we are accelerating in the negative direction. So, like,
Imagine you're backpedaling, and you're just starting to backpedal faster. You're still speeding up, but you're speeding up going backwards.
You can still.
Sorry.
Like, okay, imagine you threw your car in reverse,
Yeah.
and you slammed down. You're moving, your velocity is negative, because your car is going in the negative direction, but you're also speeding up
But
negatively.
acceleration is negative.
because you're speeding up negatively.
It's-
Your rate of
it's
change is in
values.
the negative direction.
The negative sign isn't a value, it's a value.
Okay, sorry, in physics too, we.
Yeah, it's not like physics where negative acceleration means decreasing in speed. It's not like that.
Like negative acceleration.
Means you're
Yeah.
slowing down.
Okay.
It's not
Okay.
It's direction rather than.
Sorry, I dropped physics too because, yeah, that's why.
Forget the vectors. Forget the lines with the arrows that we did in physics.
Okay, this is just another way of doing all of that.
Yeah.
Okay? Whether you do it the physics way or the calculus way, all right, you're still going to get speeding up and slowing down the same. But I want you to do it the calculus way
Yeah,
in here. Don't try to be clever.
If you try to come back.
Yeah. Okay. So, let's look at this. All right. Here I have this nicely laid out for us. Okay. Our function, t cubed minus 6t squared plus 9t minus 3. Okay, so I have things asked in a certain order. All right. First, let's find the velocity and acceleration functions. Okay. Aaron, Lawrence, what is our velocity?
3t squared minus 12t plus 9.
Great. Maya, what's our acceleration?
6t.
Good. Okay. I'm gonna go ahead and say that time is measured in seconds, distance measured in feet, right? Part B, find the position of the particle at t equals 2 seconds. What am I gonna do? Okay, we're gonna plug 2 into our position, S of 2. So we have 2 cubed minus 6 times 2 squared plus 9 times 2 minus 3. What is our position at 2? Okay, what does that mean?
It means that you're 1 foot backwards.
1 foot to the left of the orbit. 1 foot to the left. All right, part C. What time is the particle stopped? How do I find where our particle is stopped? Where our velocity is 0. So our velocity equation was 3t squared minus 12t plus 9. I want to know where that is 0. What should we do first? We should factor out a 3. Then so our particle is stopped at t equals 1 second and 3 seconds. Our last part, when is the particle speeding up and slowing down? What do I need to compare for that? We need both velocity and acceleration. So let's work on velocity first since I have it right here. Okay, so I'm going to label this velocity. We're stopped at 1 and 3. Between 0 and 1, positive or negative?
Positive.
1 and 3? 3 and whatever. Positive. Okay. Acceleration. When is our acceleration 0? I think we can do that in our head. What? 2. So between 0 and 2 we are, and 2 to wherever, we're positive. So we are speeding up when our signs are the same.
1, 2, 3.
Between 1 and 2 and
3.
and greater than 3. I'm going to write it differently this time. I'm going to write them with T's.
We're going to give you for speeding up, we try to greater than less than.
Let me see what I do in my on my keys for the homework. Okay, yeah. Let's go ahead. Let's write it like this. Okay, where are we slowing down? Because I really want to emphasize this is what when T is doing whatever it's doing. Okay, so we have opposite signs.
Less than 1.
Okay, make sure it's between 0 and 1 though. Okay. Right, because we don't have negative time. And okay, between 2 and 3. The next thing I want to look at is finding maximums and minimums. Okay? Now, you say maximums and minimums. That's not a big deal. However, we're going to throw maximums and minimums in places that might be They're gonna make you think a little bit, okay? Finding the maximum of a function, not a big deal, okay? But what I'm going to present you with are either maximum speeds or distances, okay? We're still going to have to look for critical points, but we just have to be careful of what function we look at critical points for, okay? So if we're looking for like maximum distance, we want to look at the critical points for the derivative of our position, okay? So if I'm looking for maximum distance, I am looking for where is our particle changing direction, right? And then that will tell us where we've maxed out as far as we can compare our minimums and maximums together, our critical points position to figure out where are we the furthest from the origin, okay? So let's talk about that. Okay. I want the maximum distance from the origin here. Okay. Now I am talking about distance, so it is okay if it's in the positive or the negative direction, right? We can be 5 feet to the left here and 3 feet to the right here, but we're further away when we're 5 feet to the left. Does that make sense? Okay, so if you have two critical points, you will need to compare them. All right, so here is our position function. I want the maximum distance, which means I'm looking at the maximum of the position function, right? So we need to find the velocity. What is the velocity? Okay. All right. Now we want this to be 0. And where does that happen? Okay. 3 So this is our critical point. What's happening to the left of 3/2? We're increasing to the right, decreasing. So we have a change in direction here, right? All right. It's our only change in direction, so obviously we're going to be the furthest away when we are increasing in position. We stop and then we decreasing in position. We're going to be the furthest away. So what would our maximum distance be? How would we find that? Good. We're going to need to plug 3/2 into position. I would like you to actually find it. We can maybe do it without a calculator. What's 3/2 squared?
9/4.
So 9/4 times negative 16?
That's negative
36.
36.
Negative 36 plus 48 times 3/2.
That's just 24 times 3, which is 72.
Okay, so negative 36 plus 72?
So that's 64 plus. It's 64 plus something.
That's 36. It's 28.
Is that right?
Yeah, 52.
Okay, you can use a calculator. Okay.
36.
Okay, last one. I want the maximum speed. How am I going to maximize speed? The derivative of what?
Second derivative is good.
Okay, if we want to maximize our speed, that means we're on the velocity equation, right? Which is what?
Same thing.
Oh, sorry.
Negative 32t equals 48.
I forgot that this was the same function. So then, if we want to maximize speed, we want the derivative of our velocity. Okay. Well,
Yeah, I got it.
okay. Do we have a critical point of our velocity function?
No.
Which means what is happening?
The velocity is constantly changing.
Okay. Our velocity is constant. Our acceleration is constant, right?
Yeah.
Okay. So,
Already, displacement change.
okay.
Distance
So,
changes. 3/2.
we're never going to have an acceleration of 0. But look, we're on an interval,
Yeah.
right? So we don't have a critical point, but we're on an interval. So what should we do with that interval? If we're finding a maximum
just
on
value.
an interval, what do we have to check?
The ends.
The endpoint. Ooh. So if we're talking about speed, we're talking about the absolute value of velocity. Okay. So the velocity at 1/2 would be negative 16 plus 48, which is 32. Okay. And then the absolute value of our velocity at 2 would be negative 16, right? Negative 16. Okay, which means our velocity is 16. Sorry, our speed is 16. So what is our maximum speed? Okay, so our max speed, you're also going to see a lot of meters per second. You're going to see either feet per second or meters per second. Kind of forgot about the meters. Okay, you'll see both. Okay, so I have a nice little worksheet for you here. And little may be a deceiving word.